All right.
Oh, dude,
yeah,
I didn't
I
have
need to
a
do
blue
that.
flag. Dude,
It's fine.
Do you have a meeting flag? And is it up on the site?
Did we also get our crypto challenges out?
What?
Like on to CTFD, the crypto challenges?
Yeah, my other crypto challenges are up.
Okay.
So, apologies for the delay, everyone. But
Alright, we're
it
recording.
looks like we are live? Question
We
mark.
are live.
Am I talking into this? Am I talking to this?
You want to talk? I can hear it. You want to talk in the direction of the screen,
of the screen?
like of the laptop.
Very cool.
Because
Okay. Yeah, sure.
just because when you talk in the opposite direction, the mic is not picking it up well.
Nice. Okay. Yeah, so I'm just gonna go ahead and get
Go ahead,
started.
get started.
So our presentation today is going to be on factoring numbers. And before we go to the next slide, I should give a bit of context as to why I'm giving this talk at a computer security group and not like a math group. So one of the leading cryptographic schemes that is used today is called RSA. And if you attended the crypto seminar last semester, or generally, if you've looked into RSA, you can recall that the security in RSA revolves around the problem of basically factoring big numbers. So, for example, if I told you with a calculator, can you give me 13 times 37? That's a pretty easy problem, right? But if I asked you to factor some huge number, it would be slightly harder. So the kind of hardness in that problem allows us to basically hide messages. So in this talk, we're kind of going to discuss various ways of attacking that problem in order to attack, primarily to focus on attacking that cryptographic scheme. So we go to the next slide. What better way to start any talk than with a quote by Gauss? I'll just read it off here. The problem of distinguishing prime numbers from composite numbers and of resolving the latter into their prime factors is known to be one of the most important and useful in arithmetic. It has engaged the industry and wisdom of ancient and modern geometers to such an extent that it would be superfluous to discuss the problem at length. Further, the dignity of the science itself seems to require that every possible means be explored from the solution of a problem so elegant and so self-evident. So if such a huge mathematician like Gauss is saying this, it means you probably can make a presentation about it, which is what I did. So section 0, some kind of mathematical preliminaries. Before I kind of get too much into the meat of the talk, there is some math ahead. However, if the math kind of scares you off, please try to stick with it and kind of just get the highlights. If you can just kind of brush aside the math and stick to the highlights, that would be good enough. Next slide. So prime numbers. If you've taken like a discrete math class or anything like that, you may recall that a prime number is a number that its only divisors are just one in itself. So some examples of prime numbers there, 2, 3, 5, 7, etc. Basically, reason why primes are important is any number can be factored into primes. So when we say we want to factor a number, typically we're asking, we want to factor that number into its prime factors. Next slide. So modular arithmetic. We say that x is congruent to y mod n. That's how you say that equal symbol if n cleanly divides x minus y. That kind of equal symbol with 3 lines, we use that symbol because it has similar properties to the equal symbol, because you can add, subtract, and multiply on both sides. The inverse is like division is kind of tricky because you can only divide if the number and the modulus share no divisors. So this is kind of going to be important later on. That's just the preliminaries. We'll kind of use a little bit of that later on, but just gonna stay with it. So section 1, just some basic algorithms, like how, if you gave me like a relatively small number, how would I try and factor that? So as a first kind of naive approach, we can just start to divide numbers and just see if they go in to that number until we could find something that works. But you can also see that any factor of the number will also have another divisor. Like it'll also have a bigger factor. So like if you have like a 72, for example, right? 2 will divide 72, but you also have 36 divide into 72. So you only really need to check up to a certain bound, which is a square root of it. So actually, as we discussed earlier, you only need to check like primes up to that square root. Next slide. There's actually a fast way of determining the primes up to a certain limit. It's called the Sieve of Eratosthenes, some ancient Greek guy. Say you have all the numbers from 1 up to a certain bound. You can go to the next slide. You first mark off like the first prime, which is 2. So you basically say, okay, any number that's divisible by 2 is not a prime. Okay, next slide. Then 3 is the next prime. You mark off all numbers that are divisible by 3. Next slide. Similarly, you keep going. 5, next slide. And 7, and back. And then eventually, like all your numbers that are unmarked are just your primes. Yeah. So that's kind of the basic algorithms that were used before factorization became a problem that was attacked due to the development of RSA. Next slide. Kind of a brief aside, as like mentioned, like that quote by Gauss, this problem was a problem before you could kind of just type in the Wolfram alpha or like in your computer, hey, I want the factors of this number. This is a problem that was attacked, or this is a problem that that people tried to do before the invention of computers. So I wanted to mention 2 examples from before computers. One is 2 mathematicians, Euler and Fermat. So basically, Fermat was a mathematician, and he was like, I think that all numbers of the form 2 to the 2 to the m plus 1 are prime. And then Euler was like, you're wrong. And he showed that in the case of m equals 5, with some fancy math and a bit of division, you can see the direct quote from his letter there, that basically the conjecture failed. The numbers of this form, people try to factor numbers of this form like in the later years. Obviously, Euler can factor numbers bigger than this because he was working on paper. He didn't have access to a computer. But later, as people had better and better computers and better algorithms, they tried to factor larger and larger numbers. So we can go to the next slide. There's like this mathematician named Lemmer, and I think if you think I'm excited about integer factorization, he was really excited about integer factorization. This is an excerpt from one of his like memoirs. He basically like so he was also not before, like he was around the time like where computers were like just beginning to come into play, but he used like, this is an example of like one of his, like I think it's a replica of one of his devices that was made. You can see it's like made out of like bicycle shades and pulleys and random, basically like junk you find in his garage. And he kind of like made these devices to like build devices that would factor big numbers. And you could actually like back in the ye olde days before computers, he like would publish these books of like up to 200 million of like, hey, here are all the numbers up to 200 million. Here are like all the prime factors. This is like before computers. So I thought that was kind of interesting. Before we go on, are there any questions? I'm just gonna check Zoom chat maybe. Sure. So I guess now we can actually go into some of the actual algorithms that are used today. So it's one of the algorithms, like the algorithms kind of depend on the size of the factor that you're trying to extract. So there are different algorithms depending on if you're trying to extract a small factor versus a larger factor. So if we can go to the next slide, one of these algorithms for like a small factor is a Pollard Rho algorithm. So let's say that the number you're trying to factor is some number p times a number k, where p is relatively small. Let's say you also define like this function f. It can really be any kind of function. Typically, it's defined as this x squared plus 1 mod n. But it can really be anything. Anything reasonable. Next slide. And what we do is we kind of iterate this function. So what we do is we kind of take some initial value, x naught, in this case 2, right? And then you kind of iterate that function. Like implicitly, what also is happening is you also have the sequence x0 mod p, x1 mod p, and so on, right? After a certain amount of time, however, like there's only, if p is reasonably small, there's only so many values mod p that sequence can have, that sequence at the bottom will eventually cycle. Does that sound reasonable? Yeah, so it'll eventually cycle. Let's go to the next slide. This is an example of the n at the top is what we're running the algorithm on. You can see there's 52051 is our relatively small factor. And you can see that like the start is like the tail of the big wispy thing. And you can see that it does eventually cycle. The reason this is, do you have a marker by any chance? Yeah, apologies. Oh, damn. It's chill. The reason this is called the Pollard Rho algorithm is the Greek letter rho is actually, it's the one that looks like a P. So you can imagine like, you can imagine like, put on your like abstract art glasses, but like, you can imagine like the tail of the row being like the wispy thing and then the circle. I don't know, mathematicians and their naming schemes. So like P is reasonably small, right? And if we go to the previous slide, the sequence x0 mod p, x1 mod p, you can kind of think of these as like just, for lack of better terms, just like a random sequence mod p, right? So just imagine like you're generating numbers from 1 to p just randomly. Eventually, you're just gonna come across like the chances that you're gonna come across like a cycle, which is like you're gonna hit the number, you're gonna hit a number between 1 and p twice in a row, or like not twice in a row, but like it'll loop eventually, right? Yeah, that's what the circle is. Yeah, it's a representation of the cycle. Exactly. Okay. Yeah. Yeah.
When you say it's p times k, is that p instead of its prime?
No, p is, it doesn't necessarily have to be prime. At least I don't think so. Yeah, so this algorithm is actually, go to the next slide. It's actually reasonably like fast. This is a Python implementation. You can see it's just like 8 lines. And it's reasonably fast as well. You can see here, like it doesn't take up that much space. And if you go to the next slide, it's actually used to factor the 8th Fermat number. Told you we'd be seeing those again. You can see like the actual number, it factors into a relatively small part and a larger part, like the 16 digits and the 62 digits. Next slide. Okay, elliptic curves. If anyone was at the seminar last semester, you remember elliptic curves. Essentially, what an elliptic curve is you can see the equation at the bottom there: y squared equals x cubed plus ax plus b. You can see varying parameters of a and b there, right? And you these are various plots of like on your x and y axes. If you go to the next slide. So what's interesting about these kinds of curves is that you can kind of define an addition of points geometrically. So you can define the inverse element by reflecting over the x-axis, and this addition of p and q as shown on the diagram there. However, you can kind of abstract this. If you go to the next slide. Typically when dealing with elliptic curves, either with the cryptographic scheme that uses them or with the method for factorization that we're describing here, you don't really deal with elliptic curves where your inputs are real numbers. Instead, what you do is you take your inputs to be integers mod some prime or mod some integer. So you can see here, for example, the elliptic curve on the left is y squared minus equals x cubed minus blah blah whatever, right? And you can see it's this nice plot thing that you might get from a graphing calculator, right? But on the right, it's like just a collection of points, because you're basically just going through x is just from 1 to 89. You're seeing what value of y corresponds to that. Any questions? Sure. Yeah.
It's the same equation, except on the right, every single thing.
Yeah, exactly. Yeah, so Z80, yeah, question in Zoom chat. Z89 is basically just the integers mod 89. So like 0 through 88 technically inclusive. Yeah. So if we go to the next slide. So if you actually work out the formulas for the sum of 2 points, it turns out that you need to calculate multiplicative inverses. So like 1 over something. So this is typically fine when you have like a real number, right? So like 1 over pi or like 1 over a half, right? It doesn't always work mod n though. So if you have like integers mod 32, all in it, like there isn't an integer, there isn't an integer such that when you multiply by 2, for example, it equals 1 mod 32. So it sometimes fails. However, like the fact that it sometimes fails can actually give us a factor of n. So the way that this elliptic curve method for factoring works, you basically just define an elliptic curve where the inputs are just mod n, and then you just do a bunch of multiplication on it. And then if it breaks, then you know, like when it breaks, the inverse, like it breaks because you can't find an inverse. When you don't have an inverse, you basically have a factor. So go to the next slide. This method can actually find larger prime factors than the algorithm we discussed earlier. You can see here it was used to the factor F10 and F11. And you can see like they're relatively small factors as well, 8, 9, and 21 digits, which is small, small, considering the numbers we're gonna get into. Yes.
That's not 2 numbers, right? There's 4 numbers, right? 1, 2, 5, and the bottom one. Maybe I'm just confused. But shouldn't that number be the multiplicative of 2 prime? Or is, oh wait, no, this is just for Fermat's theorem wrong.
No, yeah, no. So basically, like this is if you take like 2 to the 2 to the 10 plus 1, it equals that number times that number times that number. Yeah, all of those numbers are prime. So like,
Oh,
so like
this
this
number
number
is
is
prime.
prime, this number is prime, this number is prime. Yeah, so when we factor a number, we're factoring it into primes, right?
Got it. So
these are the primes that
you
are
take that number, you take that number and then break it down.
Break
and
it down
keep
into primes.
breaking it down until it's just prime.
Yeah, exactly. That's the whole task of factorization.
Got it.
Okay, we can go to the next slide. Okay, so this kind of works. We kind of mentioned the smaller factors, right? What if, like, if you're generating, for example, an RSA key, this is why you don't have smaller factors. Typically, what you do is you generate two primes of the same length, of the same bit length, and you multiply them together. So algorithms like this aren't really well suited for numbers like that. So what do you do in this case? So we're gonna kind of get a little interactive. Can anyone factor this number for me? Oh, that's true. What?
61 and 79.
Hey, no Google. No Google log. That's in your head. Oh, paste. You can screen share paste. Okay. So anyone can factor this without using Google or Wolfram Alpha or whatever, Sage or whatever. Okay. Can you show your work? Okay. Show your work. I'll be like that pissy math teacher. Okay. Do we have any takers in Zoom? Guess not. I'll give you a hint. Does that give anyone a hint? Does it make it any easier for anyone on Zoom? Difference of squares, exactly. Yeah, so this is 70 squared minus 9 squared, get a factor. Yeah, exactly. Yeah, so what? Yeah. So in general, if you don't know this identity, I'm going to, let's see here. Where's the paint? You don't know their prime, but in general, this is the zooming, right? We're zooming. Okay. In general, a squared minus b squared is, oh my God, Husnain's Math Academy over here. A plus b. Oh my God, this is so bad. A plus b times a minus b. Thank you very much. Okay, something like that. A plus b, a minus b. Product of those, you take that and it works. Something like that. So yeah, I don't want to save that. No one needs to see that again. Yeah, so you can factor numbers this way is the main takeaway. Next slide. This is an example of Fermat's method of factorization. It doesn't work in general though, because that was a trick example, right? Like I just kind of made that example work. It does work in general, but it's hard to find integers x and y such that that works, and the integers are reasonably small. Like it's hard to find those integers, right? Next slide. Let's just kind of try it for this integer n here. So we have n equals 1791. And let's just try. Here 41 is significant because 41 is approximately the square root of it. So let's just try to, so 41 squared is 32 mod n, 42 squared is 115, 43 squared is 200. Are any of those squares? You can take the square root, check for yourself, but none of those are squares. We are sad, this doesn't work. However, you can notice that 32 times 200 is 80 squared, right? So you can combine these congruences. You can check the math later, but basically you can kind of combine these congruences like this to show that 41 squared times 43 squared is congruent to 80 squared mod n, right? So now you have this difference of squares again that you can use to find a factor of n. So you have 114 minus 80, 150 plus 80, and you get 17 as a factor of n. Does that make sense to everybody? Cool. So we've kind of shifted over the problem of factoring numbers with this like method of two squares, difference of two squares, to like picking congruences. So the question now is like, how do we pick those congruences, right? We kind of shifted the goalpost. So now I'm going to define some concepts here. Define an integer to be B smooth, wrapper name. If none of its prime factors exceed B. So like, for example, the number 36 is 3 smooth because it's 2 to the 4th times 3 squared, right? So none of its prime factors exceed 3. So through sieving, so recall the Sieve of Eratosthenes that we discussed earlier. It's a similar process. We can get pairs of integers xi and yi, which is equal to xi squared minus n, like similar pairs that we discussed earlier, such that xi squared minus n is B smooth. Okay, next slide. Let's say we have a set of pairs, x, like those set of pairs. To get a successful factorization, we need to pick a subset of yi's such that the product of them is a perfect square. Okay, how do we do that? Next slide. So since the yi's are B smooth, we can write them as their prime factorization, right? So we can kind of take the primes under B and then write them as like P1 times E1 times like 36, for example, right? We have 2 to the 4th times 3 squared. We're next going to define the exponent vector to be just the vector of the exponents. Here, mathematicians did a good job at naming things. So for example, 36, the vector would just be 4, 2. Yeah, so next slide. No, 2 to the, wait, it's 2 squared. Yeah, thanks. Math majors can't do math. So why do we use this exponent vector? If I had more time, I'd do this more interactively. But basically, you can see the proof on the slide here. But if you recall from algebra, when you multiply 2 powers like x to the a times x to the b, you add the exponents, right? In the same way here, you basically, when you multiply 2 values of y, so like ya and yb, that corresponds to adding their exponent vectors. Does that seem reasonable to you guys? Very cool. Okay. The perfect square part corresponds to the fact that all of the entries of the exponent vector are being even. As like when you square something, all the prime powers get multiplied by 2, so they become even. So like, not next slide yet. So we kind of, why am I doing all of this, right? I've kind of took all of this vector stuff with, I'm going to take the sum of all these vectors, and I want all the entries to be even. The thing is, nobody expects the linear algebra, right? Using these exponent vectors, we can kind of recast this problem as a problem of linear algebra. So with linear algebra, we can kind of take these vectors mod 2 and use stuff from linear algebra to find a sum of these vectors such that their sum is 0, basically. Additionally, stuff from linear algebra tells us how many relationships we need to find a sum that sums to 0. Next slide. So this algorithm is called the quadratic sieve because we're sieving for quadratic stuff. Very good name. You can see an outline of the stuff here. So you choose a bound B based on your input. You sieve for smooth values of your x and y i's. You use the linear algebra and then use the method described before to get a factorization of that. Is there any questions? Okay, cool. Next slide. So very cool application. I think it's like Martin Gardner in his column Mathematical Games. I forget what year, but he basically encoded a message with RSA, and basically offered $100 to whoever could decrypt it. And you can see the quote on the slide there, but Revest is basically the R in RSA. He was like, this is going to take 40 quadrillion years to decrypt this using like state-of-the-art technology. If you go to the next slide, plot twist, it did not take 40 quadrillion years. It was factored by a team of researchers. The secret message, as you can see the title of the paper, the magic words are squeamish ossifraga. I still don't know what that is. Basically, they use like a team of computers like connected over the internet to do the sieving part, because the sieving part is very parallelizable. You could do it in parallel very easily. Then they did the linear algebra on, I think, a supercomputer. Refer to the paper. So we can actually improve this quadratic sieve algorithm because your candidates are, if you go back to the algorithm, they're about the size of root n. You want to, if you could reduce the size of those candidates, that would be really cool because smaller integers tend to be smoother. So if we could reduce the size of those candidates, that would be really good. Next slide. So enter the number field sieve. This is the current fastest known algorithm to factor numbers. It finds these perfect squares in what are called number fields. Next slide. I'm just going to skip this slide. There's more math. You guys don't want more math. And math. No more math. Wake up, please. No, we're going to get to security now. Please don't. Applications. We're at School of Engineering, right? Application. Let's go. Okay. So over the last couple of years, we've been able to factor larger and larger numbers. You can see here, like, these are basically like the largest factoring, like the RSA challenge numbers, basically like the RSA Foundation, I think, they put out a bunch of numbers. They're like, please factor these. We don't know how hard RSA is. Factor these. And these are the dates that these numbers have been factored. You can see like trend goes upward, time, bigger factor. Very cool. Next slide. And nowadays with like modern day software, you could factor numbers pretty easily. So I benchmarked like 3 different open source programs. One is Sage. It's an open source Python package with a bunch of extra math stuff. Another one is GP. I use this quadratic sieve implementation. It's like C with a bunch of math stuff. One is Cato NFS, implementation of that number field sieve algorithm I talked about. You can see like we're able to factor like numbers of 400 bits in about like 3 hours. You are able to factor like numbers of 512 bits in a couple days, given like 8 cores. Yeah.
So with in the previous slide.
Yeah.
So the academic factoring efforts, it's just like someone produces a like, here's an 800-bit number, right? Like, here's an 800-bit number, factor this.
Yeah.
Like, it's just a random number. There's no significance to that number.
No. they just took like 2 random 400-bit primes, multiplied them together, and it's just like factor this.
Got it. So someone knew that it was 2 random 400-bit primes.
Yeah.
Got it.
Yeah, and like it was mainly used to see like how hard is it to factor, right?
What's the runtime of proving a number to be like prime?
Proving, so actually that's a good question. So proving a number to be prime is known to be polynomial. So actually I think it's the AKS primality test. You can Wikipedia that later, but it's known to be polynomial. That's actually, I don't think that's like the test that's used most often, but it's known to be polynomial. And it's pretty fast.
Go through like polynomials in like n squared.
I forget the exact polynomial, but it's polynomial. But factoring, I don't think is. I mean, well, the number field sieve is definitely, it's not polynomial. It's sub-exponential, which is like, means like it's not like so exponential, the number of digits. It's like slightly below that, but it's nowhere near polynomial. Good question. Next. TI signing controversy. So basically, the TI-84, like TI didn't want people messing with the OS. So basically what they did was, in order for you to modify the OS, like the OS had to be verified with a 512-bit RSA key. Remember how I said you could factor a 512-bit RSA key like on modern hardware like with 8 cores in like a couple of days? In 2009, it took like 73 days, but they factored it and like broke the key. TI didn't really like that, led to some DMCAs. So that was the whole thing. Yeah. So I mean, like, example of like weak keys. I mean, I don't even think anyone uses 512-bit RSA these days. Don't do that. Yeah.
Also a really famous one where it was like someone had it was like the DVD.
I think I read it. Yeah.
And it was something like only 40 bytes. It was like it was like super duper short. And they factored it in like 28, like a long time ago. And then they put the hex in the 2600 hacker magazine. And 2600 got sued. And I think they won. I don't remember the details, but it was an interesting case. And it was because the key was only like 40 bytes. It was either 40 bytes or 40 bits.
I want to say I can factor a 40-bit number like with paper and pencil. So I don't know. Next slide. Oh, okay. So this is like an attack that was found in 2015, the so-called freak attack. Basically, like this was an attack found on many mobile browsers and desktop browsers. Basically, like there was a mode that forced the browser to use 512-bit RSA. And there was a man-in-the-middle attack found that basically, if used, would force the browser to use 512-bit RSA, which, as discussed earlier, would not be good. It would lead to all of your messages. I mean, not all of your messages. I mean, it's still somewhat hard to factor 512-bit RSA, but definitely a security risk. Next slide. So all this talk about 512-bit RSA keys, there was a paper published like 2015-ish discussing like how common are 512-bit keys like on the internet. In 2015, they were quite prevalent. Here's a graph with their data. You can see like on the bottom, that's not readable at all. But you can see like on the red is HTTPS, the blue is SSH. The blue is DKIM, and the green is SSH. The right is 2 to the 9 bits, just 512 on all of those.
No, it's not.
Sorry?
Like one little thing.
Yeah. Yeah, that's not good. Like you can factor that, like that's not good. They were prevalent. If you go to the next slide, I did a scan on Census, which is like a service that like basically scans like a lot of IPs for SSH keys and their sizes like this month. And like I mean it's gotten better obviously because of like recommendations to use 2048-bit keys. You can see like the average size is 2048-bit keys, but you can still see like there's I think like 0.1% or something like that of like 512-bit keys that exist still. Next slide. That being said, things can still go wrong. So this is an example of like some ransomware that you can see like there's like a hex dump of the actual ransomware, and inside the hex dump is a public key, but due to some formatting issues, actually I think the first version of this, like they just said they were using RSA to 124-bit, but they're actually just using AES, and the decryption key was just in the binary, so you could just decrypt it. But then like they were like, okay, we got to fix it. So then they did this, like they actually started using RSA, but like the formatting was wrong. So they actually they ended up just like effectively using a 512-bit keys. That's obviously factual. Next slide. I mean, I guess ransomware makers like don't know how to use RSA because there's another ransomware thing that claims to use RSA 1024-bit. You can kind of see it in the screenshot there. But if you actually do some analysis on the binary or like the files that it produces, it doesn't use a 128-byte modulus. It uses a 128-digit modulus, which is like not the same thing at all. Like one is very easily factorable and one is like not factorable at all. Yeah. So be careful when making your RSA stuff. Yeah, so I just want to spend the last bit of the talk talking about the future. 512-bit keys, clearly don't use them. 1024-bit keys. So even back in like 2003, the Shamir, like the S in RSA, was like, you should probably not use 1024-bit RSA. He, in this paper, described a theoretical device. It's really interesting. It's like using optical computing and like really cool stuff. But basically, they described a device that basically would cost like $10 million to factor a 1024-bit modulus over a year. So, and sieving is the step that takes like the most computation relatively. So if you're trying to encrypt secrets against like a nation state or someone with that kind of money, don't use 1024-bit RSA, I suppose. Next slide. So you might have heard about like quantum computers breaking cryptography. This is kind of true. I mean, it is true because on quantum computers, there's an algorithm that exists called Shor's algorithm that can basically factor numbers in polynomial time. Briefly, without getting into too much detail, the algorithm uses quantum magic to find the period of the sequence to find a non-trivial square root mod n. So it's very similar to the sieving algorithms we discussed earlier. Next slide. However, like due to the size of like the quantum computers needed to factor like the 1024-bit keys and the 2048-bit keys that we use today, and the amount of like you need this quantum computer to be like to have like no noise at all and like no like otherwise the bits would like decoherence and all that good stuff. It's not practical right now to factor like any numbers bigger than like a few thousand. Yes.
Have they done any factoring yet on quantum computers?
Yeah, but like the biggest number is like a few thousand.
Has that been increasing pretty rapidly? Like, was it at a few hundred? If you like,
So I mean, actually, there's a link at the bottom that, to a DEF CON talk about this. Essentially, it has been increasing a little bit. Like recently, there's been developments and algorithms like on how to decrease the number of qubits needed, like or quantum bits on your computer, on your quantum computer, sorry, that are needed to factor an integer, even with like a certain amount of noise. So there has been developments, especially, and this is not even attacks on RSA, right? So like you can also use things like, I know Grover's algorithm. You can also use that to basically attack. You can use that to attack symmetric schemes like AES as well. But asymmetric schemes are more vulnerable because Shor's algorithm also attacks things like ECC because it can be used to solve integer factorization. But it can also be used to solve like the discrete log problem. That makes sense. Yeah, next slide. Takeaways. Factoring is hard. We use this to hide messages. RSA can be vulnerable, not only due to short keys, but other methods as well. Bad primes is like you're done. Use elliptic curves, preferably. It's more efficient. I mean, it's obviously still vulnerable to attacks, but it's generally more efficient. And most cryptographers that I've seen recommend ECC over RSA. And quantum will break crypto soon, trademark. Yeah, that's the last slide. Are there any questions or comments or concerns? Threats? Yes.
Can a elliptic curve cryptography be broken the same way that RSA can with like quantum computing?
Yeah. So from my understanding, the thing that makes Shor's algorithm works, that makes it English today. But the thing that makes Shor's algorithm work is like an attack that can also attack the discrete log problem, which is what makes ECC hard. So it can also attack ECC as well. So there's all this discussion about like post-quantum cryptography, right? Which is something I don't know that much about, frankly.
Like NP hard, that was my question. Post-quantum. Is it just like run an encryption algorithm that's NP hard?
I suppose. I hope Jack is still in here because he'd be able to answer this more. But I think it's stuff like that. Yeah. I mean, for symmetric schemes, from what I remember, like stuff like AES, right? Basically, like your function, like for symmetric stuff, there's an algorithm called Grover's algorithm that basically will effectively reduce your key size in half. So like for that, you just double your key size. So like instead of AES 128 bit, you just do 256 and you'll be fine. I don't know what yeah, that's the meeting side. In terms of like RSA, we could use bigger numbers, but it seems like the polynomial nature of it means that we would need a lot bigger numbers. Although I don't know that much about quantum stuff, to be fair. Any other questions? Zoom question.
What was this question?
Oh, can quantum computers theoretically break all encryption or some immune? Oh God, this is like the one thing I don't know about. On the bottom of the quantum slide, there's a link to a DEF CON, some DEF CON slides that have more information. But from my I don't even understand quantum computer. I mean, same, but like, so like theoretically, a classical computer could theoretically break all encryption, right? It just takes time. However, like it's the thing with quantum is that it introduces new algorithms that have different complexities. So like Shor's algorithm is polynomial time for factorization, right? So if we have a big enough quantum computer that can factor like 1024-bit number, that's a problem. Quantum cryptography. No idea how that stuff works though. I don't even know what that is, frankly. Yeah, I mean, theoretically, you could just like encode an NP hard problem into a cryptographic scheme and just have that. Yeah. I think there are some encryption methods that haven't been broken efficiently. What the? Okay. Something about spins on qubits and verifying those spins on target. There doesn't seem to be many implementations of state-of-the-art factory. Do you think there's software? Okay. 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 There's a lot of questions. So in terms of Stroya, there is a lot, many implement. Okay, good Lord. Okay, Stroya. I did do some reading on like there's some I read a paper on like FPGA implementation of like the elliptic curve method, for example. There's too many implementations. I mean, I don't know enough about implementation. I'm a math major. I don't do implementation. But the implementations that I've seen seem pretty good to me. But you could, like, if you could implement this stuff on like FPGAs, especially stuff with like the number fields, like what is it? The TWIRL device, making that on like a FPGA or similar devices, that could potentially be an avenue of improvement. What else? I think there are some encryption methods that haven't been broken efficiently on quantum computers. Which division is quantum computer? Apparently, quantum computers can't break AES and Pollard Rho. Yeah, so I mean, AES, to break AES with a quantum computer, you would just, from my understanding, you just use Grover's algorithm to kind of just solve like, because Grover's algorithm basically just finds an inverse image of the function in root n time, if I remember correctly. So where's my camera? Is it there?
Yeah.
Okay. In root n time, so you would just do it in root n. You would just like effectively halve your key size. Do you have any questions in the room? Very cool.
Great. Round of applause.
No one fell asleep. Very cool.
Oh, really good.
Oh yeah, by the way, I have an implementation of like a lot of these algorithms on my GitHub as well. That's the inspiration of this talk.
What's your GitHub?
I can post it later. I think we're good on the recording. We got 15 people in Zoom. I think that's everyone we're gonna get. Everyone joined to troll that guy.